All right, I think we're going to get going. It's 9 o'clock. Thanks for coming to such an early presentation on a Thursday. It's been a long week. Oh, still have people coming in. All right. So my name is Ryan Quinn. I work for Assured Information Security on our open source Bareflank hypervisor, which is basically the first open source hypervisor to be written in C++. And I'll be talking about testing today. One of the goals with our hypervisor when we first started developing it was we wanted to be able to use it in some more esoteric type of applications, some government, automotive, medical, that kind of thing. And there's a lot of regulations associated with using something like a hypervisor in these environments. And so testing was incredibly important. And so we tried to take it as far as we possibly could. And since then, I've actually been getting quite a few questions, both internally within AIS, but also externally from other projects as to how we actually did our testing, how we pulled it off. Also questions like, what kind of an impact does the testing have on your development? And then I've since then actually had some questions on how can we integrate some of this stuff into our project. We don't really know how to do it from very experienced C++ developers too. So some of this technology is new enough that it's kind of mystical. And so I kind of want to prevent that. So I started by going to my management and saying we should create a hello world for continuous integration. Because if I can create a simple project that sets up continuous integration for various different environments and puts in as many tools as I can possibly get, then I can always point people to this project and say, this is how we set up our continuous integration and all the various different tests that we use. And if you want to be able to integrate it into your project, you can go here and see a very simple example. And so we did that. So I provided the link. I would love to get pull requests from the C++ community to further expand this project. Everything that's in there is very, very simple. The idea is to keep the examples as simple as possible. But there are a lot of other tools that are out there that we can apply to our code that I'm probably missing. As you'll see as we go along, I got quite a few, but I'd love to add as many as we can. Another goal that, like I said before, that I have with this is to very much demystify the idea of continuous integration. I think people tend to, I don't know, they see it as something that's impossible for a large project. I know when I wrote the topic, that was probably one of the biggest comments I got was, how does this apply to my large project? I'm writing, we have hundreds of people working on it, and it's, hundreds of thousands of lines of code. There's no way I could possibly do this stuff on a project of that size. And I've personally done it on large and small projects. I've worked on projects that have zero testing at all. Everything is done using manual labor and test procedures. I've worked on code like our Bareflank hypervisor, which is 100% automated with 100% code coverage. So I understand both problems, and I know the positives and negatives associated with going in both directions, because believe me, 100% code coverage does not have as much of a return on investment as you might think. I'd also like to give a quick shout out to a couple projects. I've been working with Jim from A-Style. He's fantastic. I'm a big fan of A-Style, and so he helped out a lot to try and get some of this together, as well as Clarity Scan. They actually made an exception for this Hello World project. They don't normally allow Hello World projects to go through their servers, but they made an exception for this one. And also the GSL. Neil is fantastic. If you haven't used the GSL, you should be. So go ahead and take a look at it. And Include OS, just because I love that project. And if you haven't seen it, go take a look. All right, so we're going to start off by creating an open source project. So us as a group, we're all going to do this together. We have this critical requirement from our customer that we have to be able to create this application that can print hello world. And so we're going to create a producer. He spits out hello world. Very simple. We're then going to create a consumer that consumes this producer and then runs its print message program. And then finally, we'll create a main application that creates the producer, passes it to the consumer, and the consumer then does its job on construction, and the program exits. So this is a fantastic program. We were even, as a group, we were featured on Time Magazine. It's just awesome. Until one day, somebody decides that they want to change the code because they think that we could have done a little better. And specifically, they would like to be able to change the text from hello world to anything they want. And so they provide the project with a pull request. This is what the pull request looks like. So as you can see, the code's changed quite dramatically, but the theme is they're looking to allow you to create a new define that can change the text of the print message. And they're also interested in adding, or prepending, I guess, message : to the output so that it's explicit that this is a message. Now you can see from this example that the code itself won't even compile. It's missing all sorts of things. The style is very different than the style that we had in there before. It's hard to see on the projector, but there's added white space and new lines at the bottom that shouldn't be there. And this is certainly going to have problems with memory leaks and C++ core guideline compliance. So what I'd like to do, now that you've seen this horrendous example, is I'd like to take code that at least does compile and create a pull request. So we're going to go to this file. Of course, I don't have internet connection. All right, well, I'll do that later then, if we have time. But at any rate, what I was going to do is create a simple pull request so we can get that kind of kicked off, and you can see what the CI process looks like. But we can do that if we've got time at the end. All right, so without CI, and we've seen this on a lot of projects that use mailing lists, you're going to have a bunch of basically project maintainers. They're going to see this pull request kind of come in, and in the case of a mailing list, it's just going to be a patch, which is horrendous to review. And everyone's going to have to kind of chime in and explain why that code is horrendous. And everyone's got different ways of handling this. Some people are going to just slam the person that put that code in there. How dare you write such horrendous code, and the whole 9 yards. Other people will be nice and provide, decent comments and actually help guide the person to a better piece of code. But in the end, the major theme here is that this is a manual process. Everybody's got to sit down as the project maintainers and look at the code and try and find all the different problems that are wrong with it. And since they're project maintainers, they're probably very busy. So the question is this actually a good use of their time? Should the project maintainers be worrying about how many spaces are between parentheses, or worrying if there's a memory leak or white space, or should they be required to take your patch the code, then compile it and make sure it still compiles, make sure the code still runs? That's a lot of time. Even for a patch this small, you could end up with like an hour's worth of work. And for a lot of people, that's a lot. Another thing is, what's the likelihood that they miss something? If we all stared at that example for long enough, do you think everybody would find the same number of issues with the code? Probably not, right? The likelihood that we miss something is really high. I can say, in my experience, even with some very rigorous CI practices, with as many tests as we can throw at it, we still end up missing stuff. Now they're more structural, architectural in nature, so it's not silly things like style, but it still ends up being a problem. It's a lot of work to do a good code review. It's very hard, and the last thing you want to do is be consumed with these sort of issues that could have been spotted by tools that we already have today. And then the other comment I have is, what's the likelihood that the author of the PR ends up being offended by the comments that come in from a piece of code that looks like that? Probably pretty high. And especially for like an open source project, but even when you're working with your own peers on closed stuff at work, your goal is to try and foster a good environment. And when somebody who's a novice comes in and writes a piece of code like that, they can sometimes get lambasted pretty quick. And so if there is a set of automated tools that could tell the person, hey, you need to fix the following, before a project maintainer or some person out there had a chance to review the code, they're going to have a set of automated tools telling them that they've done something bad. And that's much easier to swallow than an actual physical person. And so by the time the project maintainers actually see the code, it should be things that are more structural in nature and likely to produce a better debate online or internally within your company. So in case you're not familiar with what continuous integration is, it's simply the act of integrating small changes into your project on a continuous basis. So every single time you make a patch, you're going to go through a series of various tests and actually do integration of that code to validate that you haven't broken anything. There's also other continuous type things like continuous deployment and that kind of stuff, but we're just going to focus on CI today. It can be considered part of test-driven development, but it doesn't have to be. The basic idea here is just that whenever you're making changes to your master code base, you're going to be continuously making sure that you haven't broken anything. There are tools out there that can help us do this. So for example, things like Travis CI, AppVeyor, GitLab, Circle CI, Jenkins. There's a lot of tools out there that you can use. We're going to, on this project, we're just focusing on Travis CI and AppVeyor because that gets us Linux, Windows, Cygwin, and OS X. But you don't need to use these tools. So for example, if you can compile on Linux, you could just create a cron job that kicks off every night and runs your master branch, make sure it compiles, make sure whatever tests you have in place actually run. And then if there happens to be an issue, you could send an email to the project maintainers and say, hey, our continuous integration server found a problem. And then you'd be able to address that as soon as the tests were done. You could do that nightly, you could do it weekly. The idea is to do it as much as possible. And setting up a cron job with an email should take like an hour. It's not that much work. So it really depends on what kind of build system you have, but I can tell you, like for us, we have a project that has very little tests, but it does build. And we do have a nightly build server that goes and takes this giant chunk of code, builds it every single night, and then reports if there's a build failure. It takes roughly around 8 hours to do the build. There's, hundreds and hundreds of thousands of lines of code, and it will only build in a very specific environment, but we still have it automated. So at least at minimum every night we know if the project compiles, which can be huge. There are open source examples of using continuous integration with a set of various different types of tests. And the biggest return on investment is going to be, can I get to compile and can I run a set of actual unit functional integration tests? And these projects that I've listed are just a very small subset, but I like it because it kind of shows various different degrees of how much tests people are running in their continuous integration environment. So for example, with Bearflank, like I said before, we have everything. 100% code coverage, static dynamic analysis, everything down to documentation and whitespace. It's actually quite painful to try and get a PR through the process. Can take as much as a day or two to get even a small code change through all the checks that need to go through, but this project has its reasons for doing so. The JSON library that I listed here is a very popular one for C++, and they leverage quite a bit of the same process. So if you're looking for another example, this JSON one is fantastic. The GSL is a good example of a project that uses continuous integration. They use actually Travis CI and AppVeyor as well, but they don't have as many of the tests that I've listed here built into their CI process. So for the most part, they're building it and they're running their unit tests, and that's about it. So this should give you kind of an example of just how far you can take this versus how far do you want to go based on your return on investment. And then finally, one note I wanted to add is that if you happen to be an open source project, there are a lot of badges that you can actually add to your project that'll help show that you're doing some of these tests. And I think from a C++ community perspective, it's probably a good idea for us to use these because it can really show how much rigor we all put into our projects. All right, so let's jump right into this. So the number one largest return on investment you can get for setting up continuous integration is hands down, does it compile and does it run? Because that can actually be quite a bit of work depending on the project. On a really small project, the amount of stuff that has to happen is probably pretty minor. But on a larger project that takes hours to build, if you have a continuous integration server that's plugged into your pull request process, then the project maintainers never have to actually pull down the code and do a compilation or run the code themselves. They'll get a report once that's done by the automated tools, and they can be rest assured that it compiles in different environments they care about. So it can save quite a bit of time for the developers. And more importantly, they won't click merge until they know that it compiles, which from a development perspective, if you're working with a lot of people, we've all been there, you go and pull down master and it doesn't build, and then you start screaming across the office, who broke the build system? Or why does the code not build? Well, this can really help prevent that. Still happens, but it can help prevent it. To do this is really simple. If you look at this example, I have several Travis CI scripts in here. This is simply YML. And so if you go to the open source project, you can see how this kind of fits in. But here I've basically defined a test that I want to run in my CI. The add-ons part is simply telling Travis CI what packages I need to install. And the environment variable at the top just labels the test, so I have a way of knowing what test this actually is when I see it on the server. And then the script part goes and simply runs cmake against our code. It then runs make test, and then actually executes the code. So it's that simple. Now, once again, like I said, everyone's projects have different build environments and different things, but once again, if you have the ability to build it, you almost certainly can get it to work in CI, especially if you have very specific requirements like we have on our larger project. Then you can do things like Jenkins, where you can create your own servers and set them up however you want and get them running whenever you need them to. So the next check here that has a really large return on investment is simply doing a white space check. So this is actually quite important because it helps prevent contamination of your Git history. So everybody's got different editors and different ways they like to code. And some people will turn on things in their editors that'll remove trailing white space. And in fact, some editors have it on by default. Other editors don't. And so you'll end up with people who are committing white space to the project and people who are then removing that white space when they make a code change because their editor detects it and removes it. And so you'll see PRs where white space is being added and removed throughout the Git history. And so lines are being changed, but that wasn't actually the line that the person was trying to modify. Instead, it was just the editors adding and removing white space. And so having in your CI process the ability to check this white space can help prevent that type of contamination. So I know, like, when I've done a couple patches to the Microsoft GSL, I have to, because I don't have this check in there, every time I do my patch, the first thing I have to do is go to my editor and turn this setting off. And then I make my patch, and then I submit it, and I have to go through the diff and make sure that I'm not adding these lines that are accidentally removing trailing white space. As soon as I'm done making that patch, I got to go back to my editor and turn that feature back on, because on other projects that I work on, we have this check and we don't want white space being added. So it's this constant back and forth. It's kind of annoying. So adding a simple test like this can help prevent that. In this particular case, we're using git check diff. There's other tools that can do this too. This is just a really simple one. If you happen to be using Git, if you run this command, it'll tell you if you have trailing white space that's in your patch, or if you have missing or redundant end of file new lines. And in our Travis CI script, it's really simple. We simply run this command, and if it outputs something, then we know that we've failed the test. If that happens, we tell the user, you failed the test, and then we actually run the command again so that they can see where in the actual patch they're failing, so where they actually added new lines and where they didn't. And then of course we exit. By doing the exit -1, Travis CI will fail the test and you'll get a nice big, X question. It is git diff -- check. Thank you for correcting that. So I'll make that change before I upload the slides. But yeah, that's an error. It should not be that. And you can see in my my screenshot I have it the right way. So I'm just dyslexic apparently. Thank you. All right. So right off the bat, if we look at our example of the person that made this horrendous PR, the git diff check will tell us that, hey, you have white space and that test will fail. And so the author of this PR will immediately get some feedback to say, hey, you need to make this change, and we'll end up with the code on the right. The next easy thing to integrate into a project, whether it's large or small, is source code formatting. So I've reviewed lots of source code. There's nothing worse than having to go through the review process and say, please remove the following, syntax, or, we don't use spaces here, we don't do that. And the amount of time it can take if the patch is really big, it's just obnoxious. But the problem is that, especially for some of the projects we work on, we don't really like having this spaghetti code of, many different developers and their coding styles. And so you can end up with this project that just has like 15 different coding styles throughout, and it's very hard to kind of follow and read and where it's going. So using a source code formatting checker, you can alleviate these types of problems. Now, the number one issue with these tools, and where you're going to end up with a lot of debate, is that they're not perfect. A-style I love. Clang format is also another option. The problem is that for as good as something like A-style is, it's not perfect. And you're going to have to compromise on something. Everybody will. I haven't found somebody who has looked at these source code formatters and said, it does everything that I want it to and it meets my personal preferences perfectly. It's just never happened. So if you're going to integrate one of these tools in, the positive and minus to this is that everybody compromises. So nobody's going to get everything they want. But it's better to have a consistent way to verify the style of your code than to get the perfect source formatting out of these tools. In a sense, the return on investment is huge when everybody basically just says, I'm going to put my hands up, we're all going to just use this one coding format that the tool is telling us we should abide by, and that's it. The argument's over. It's not perfect, but it's fantastic in a sense that it removes the debate. And every single time I put a code change in, this tool will tell me if I need to make a change or not. Very easy to integrate into small projects, and it's actually relatively easy to integrate into large projects. For the large projects, these types of tools will allow you to state exactly which files you want to do source formatting on. So in a large project, the easiest way to do it is to look at, say, for example, your manager comes down and says, we need to add the following feature. So I have to go to this piece of code and I have to go in and modify it to add that feature. So set up your CI with the source formatting and tell it to format that piece of code. Everything else gets ignored. But that piece of code that you touched, at least at minimum, now it's following that standard. And over time, you can keep adding to this until you finally have the entire project. The big issue that you also run into, and I remember last year at CppCon when we discussed some of this stuff, one of the comments that came up was, what do you do about Git history? So let's say you've got a medium-sized project and everyone agrees, let's just go through and run this tool and it's going to format all our text and we're good to go. Well, the problem is your Git history is going to get just trashed. And so there really is no magic solution to this problem. I mean, obviously, if you're going to go through and format all of your source code so that it leverages one of these tools, you're making code changes. Those code changes are going to show up in your Git history. There's no way to rewrite history. So the best solution that we have found in practice is that don't make a change like that until you start your next release. So you just got done delivering a product and you're about to throw all the developers now onto the next big task. It's going to start a new baseline and you're going to be making a whole bunch of changes over the next couple weeks or months or whatever it is you're doing. Make your source code change right before you start. That way your Git history, yeah, it's modified, but you can always go back to the previous release and see everything that was done, and then all changes from that point on, the history is fine. So that seems to be the winning combination that we've had, at least in the past. The other note I'll make is that, and one reason I like A-style over Clang format is that you really want to package up your source formatter and some of these tools in general with the environment or on a specific version and with your build system. The reason being is that if I take, say, A-style version 2.x or whatever and run it against my source code, and somebody else happens to have A-style 3.x, they're going to find different things. The same tool, same flags, everything, but the two tools, since one's updated, they may find bugs or things that weren't being formatted properly, and they'll make changes. And so you'll end up with somebody's source formatter making changes, and then somebody else is putting them back and then making changes again and putting it back each time code's being checked in. You all need to use the same version of these tools. And so just keep that in mind when you're integrating these things into your project, that there has to be a way to specifically state, I want to use this tool, this version of this tool, rather. Excuse me?
Why couldn't you do that with Clang format?
You can do it with Clang format. The problem is that if you want to package up in your build system, compiling Clang format is a pain, whereas A-style takes about 30 seconds. So it's much easier to package up A-style into your build system and deploy it with everything that you're doing versus Clang. Now you'll see, I'm not a big fan of Clang format. It's very hard to get changes into the project because they really only service large projects. But I love Clang tidy, and so we have this same problem with Clang tidy, so I'll get into that. Okay, so I'm going to show this one. I'm probably not going to do the walkthroughs for the other ones since we don't have a ton of time, but I at least wanted to show what it kind of looks like within your build system for setting this up. So if we look at our Travis CI file to start, it's really very simple. There's some stuff in here that won't make sense unless you see a lot of the other tests. But in general, we try to update the build system so that we have a newer version of CMake. Travis CI uses Ubuntu 14.04, and so there's a lot of things on there that are really old. So you'll see we're always like updating GCC, and we put in a custom CMake here. And then from there, each test just runs. The way that this matrix works is it basically says every single test that I have here for this will spawn off a new server that will then go and download my code and compile and run just the stuff that's in this block. And so every block that you have is going to be a new test. And so you'll see on the output of Travis CI a giant list of all the tests that are running, and they'll have clocks that are basically showing you the progress each test is making. So if you happen to pay Travis CI for exclusive access to their servers like Microsoft does, then when you submit a PR, you're going to see, like in this particular case, we have something like 20 different tests. You're going to see 20 servers all start up simultaneously, all running your project to compile your code and then run the specific instructions listed here in each block. And so for a project of this size, in about 2 minutes, you're going to have the results for everything all in one shot, which is fantastic. Within the CMake thing for A-style, you can see here we're grabbing the A-style code, and at the moment we're using Bearflank. That's because A-style didn't have like a CMake build system built into it, so it was actually quite difficult to get their build system integrated into an existing CMake one. So I have a custom patch to A-style to integrate CMake, and I was actually working with Jim to get this integrated. So I think in the future, real soon here, he'll end up actually having CMake compatibility. So that would be pretty nice. We can actually get rid of our custom patch. And all this is doing, if you're not familiar with CMake, the details here aren't important. What this is doing is it's downloading the code, is then going to build it and install it. And this line right here just simply says, please install it into my build directory for my current project. From there, we're going to create a custom target called format. So that allows me to do something like make format. And that's going to take the executable that was compiled or downloaded and compiled here, and it's going to run it against these A-style args, which is everything you see here. So this is where I actually define all the various different formatting rules that apply to this project. and then here's where I tell it which files I want to actually do A-style on. There's some details here that are probably important. So if you're on a large project, there are two ways you can do this. You can provide it with just a source directory and say, give me all the source code, in the following directory. Or what you can do is, which we do on Bearflank, is you can actually use Git to tell you all the files that are in your repo and then pass that list to A-style. And so anything that's being managed by your Git repository shows up in your A-style. So there are different ways of getting access to which files should I be formatting, and that's really up to you guys on just how much you want to actually do. And every single one of these is very similar. You're creating a target, you're going to integrate the tool, and then give it the parameters you want and move from there. So it's very simple to kind of set this environment up. All right. And so finally, with respect to A-style format, you can see we build the project, we run make. Make is going to not only build the project, but it's also going to build A-style based on our use of external project add-in CMake. And then from there, make format will work. So I can then run make format. If make format actually changes code, that means the test has failed, because that means that there is source formatting errors in the PR. In which case, git diff will tell us that, hey, there's been changes made to the repo, therefore the test must have failed. We'll tell the user and then do git diff again to show them which portions of the file were formatted so they know, where their mistakes were. In general, they're not going to care. They're just going to run make format and then resubmit their PR. But it sometimes helps to see. So right off the bat, if the author of the PR sees that those tests fail, they're going to run make format, and the result is on the right for our current code. Now, there is a bug in my screenshots. At this point, the code should have been able to compile, and so you'll see autobuff equals new. There should be new space char. That code there makes no sense, so I apologize for that. The next tool will integrate a static analysis. I love these static analysis tools. They are fantastic. They make such a huge difference in your projects. If you're not using them, please find a way to do it. Clang Tidy is my favorite, but I also like all the others that I've listed. CppCheck, Codicy, Coverity Scan. They're all fantastic, and there's a whole bunch of other ones. In fact, there's projects online where they'll take all these tools and run them against your source code for you. So, and they have even more than what we've listed. And so all you have to do is just submit your code to one online project or work with them to do it privately. And they'll run all these static checkers for you and validate if you have a problem or not. And it's just fantastic. These things do everything from finding compile time bugs to compliance testing, for example, the C++ core guidelines, and good, bad, and ugly patterns. So Clang Tidy is fantastic for compliance. They check for cert bugs. They check for, I think they're adding in 5.0 high integrity C++. They have the C++ core guidelines. And if you happen to be a Clang LLVM developer, they also have checks for your style guides. There's also a static analyzer that will do things like compile time bug checks. It's good. It's not the best, but to be honest, the other stuff, if you get through the compliance checking, most of the time you're not going to end up with a lot of static analysis issues in the end because the other stuff will find issues right off the bat. CppCheck and Coverity Scan tend to be better at finding the compile time bugs. CppCheck is very easy to set up. Once again, you can grab a specific version, compile it in like 30 seconds, and then just use it. Coverity Scan is a little bit more complicated. You have to submit your source code to their website. They then do a full analysis and then give you a very fancy web GUI to parse through all the errors that it's found and check them. But if you can get it set up, it's a very useful tool. And if you happen to be an open source project, it's free, so there's no reason really not to use it. This is very easy to set up on small projects, harder to do on large projects. It is, hands down, the best solution is, once again, to break the project up into smaller parts. So when every single time you make a code change to a specific portion of your large project, integrate these tests for that small part, and over time keep doing that until you've eventually got static checking working on everything. And then once again, if you look in our CMake file, we added a check target for make. And once again, it's very simple. You compile the code, run make check. That'll go through and run, in this particular case, it runs CppCheck. And if there happens to be any issues, it'll spit out what those problems are and move on from there. There's really nothing complicated about getting this going. I'll also make another note that Codacy, which does really kind of regex type checks, it'll look to see for common patterns that are good, bad, and ugly. And it'll tell you, you probably shouldn't do this because it's bad. I don't know if it's been there the whole time or not, but at least recently I started noticing that it's finding errors from CppCheck. And so if you use Codacy, I believe you'll end up with CppChecks along the way as well, in addition to the regex type stuff that they're doing. So it's a fantastic tool if you can use it. And it might save you some time because you don't have to go and do CppCheck manually yourself in this CI. So the static analysis tools are going to look at this code and they're going to find all sorts of things. Now what's cool about this is that if you look at what it's going to find, if you were to fix all the things the static analysis tool finds, you're actually not going to end up with any dynamic analysis failures in this example because it found all of the problems using static analysis. But because of that, we will not fix them all and wait until we do the dynamic analysis part of this. But you're going to find things like you should have used a unique pointer instead of new and delete. That's a C++ core guideline check. You're not allowed, if you're trying to comply to those guidelines, you're not allowed to use new and delete manually. Another one that it'll find is you should be using no pointer instead of 0 or null. And that's a Clang tidy modernization check. It's also going to notice that that if statement is always true. Reason being is that right now, since we're not recompiling this program with a different string, hello world is a const char star that always points to something. Therefore, it is never null in this example. This is due to the fact that that is a runtime check instead of a compiled time check. Therefore, the runtime check will always be true, or it will always be false. It's based on how the code is actually compiled and not how it runs. And the static analyzers will actually find that and tell you that this is always true, it's useless code. And I believe Clang tidy's performance checks will find that for you. But there are other ones that'll do it too. And so that's going to cause the author of this PR to kind of go, maybe I need to do something different here because I'm doing a runtime check and that doesn't make any sense. It's also going to tell you, based on the C++ core guidelines, that the use of sprintf is an unsafe function. It's unsafe for many reasons. One, it's not the snprintf version. Number two, it's because it uses veridic parameters. And that's not allowed, once again, under the C++ core guidelines. So right off the bat, the user is going to be, the author of this PR is going to have to rethink what they're doing because they're doing stuff that's just not allowed. Dynamic analysis is another one you can run. So when you think of dynamic analysis, think of what can I find after I execute the code. So static is done during compile time, dynamic analysis done during runtime. Valgrind traditionally was the tool of choice for years. It's a little heavy-handed. The Google sanitizers are somewhat newer, and they are fantastic, very easy to integrate into a project. And basically everybody should try and compile these if you have them. I'll be honest, I don't know what Visual Studio provides here. I know they have the static checkers. I don't know if they do the dynamic checkers. So, if someone knows of how to set that stuff up, please provide a PR to this project and we'll get it integrated. We're using AppBear and Visual Studio, so I'd love to get it in there. So these tools are good at finding resource leaks. They're good at finding memory corruption as well. So I ran over a buffer or something like that. And they're also good at finding race conditions and deadlocks. Very easy to integrate small projects. And they're actually really easy to find or to integrate into large projects. Now I have the note here that you could break it into sub-projects, but I'll be quite honest, unless you're writing really horrendous code, the likelihood of Google sanitizers finding a whole bunch of stuff wrong with your code is minimal. If it does find a whole bunch of stuff in your large project, you probably need to fix it, because if you're finding issues using dynamic analysis, they're probably really bad. Static checks, hey, that's great, it's gonna make our code a lot cleaner, probably more efficient, blah, blah, blah. Dynamic checks are gonna tell you, hey, your code is gonna like die. So you really need to probably fix anything these tools find. All right, so to integrate these in there, especially, so I basically don't like using Valgrind because Valgrind tends to have a lot of false negatives. We do have it integrated into this project, but like I said, it can find false negatives. And with simple things like just compiling a cout hello world project, it'll find stuff that doesn't exist, or it's finding issues with the libraries that really aren't issues and things like that. So it's a useful tool. If you can get it to work, great. But the Google sanitizers tend to work really well. I've really never had any problems with them. But the Google sanitizers are broken up into different types of tests, and they're based on compile flags you provide Clang or GCC. So you can't do them all at once like you can with Valgrind. So you're going to end up having multiple tests. So you're going to do one for your address sanitizers, and you'll do one for your memory, then you'll do one for undefined, and you'll do another test for thread, for the thread sanitizer as well. So here you can see I basically enable the address sanitizer, and I compile the project and run test, and then I have 3 other tests to do the same thing, but they turn on the undefined checker or the thread checker. And so the dynamic analysis tools here will identify that that new command is actually leaking memory, and that if the string happens to be larger than 64 bytes, then you're going to end up with a memory corruption error as well, because we can define string to be anything we want. There's a problem. There's also an issue due to the fact, and the static checker found this based on saying this should be null pointer, but because this is a string not equals 0, it's perfectly valid from a compile time perspective for string to equal an integer. And that's not what we want. We want it to be a string. So I could put a lot of really bad things in here and end up with a bit of a problem. I can also put in 0, or I guess it's not true since we're doing the check. But at any rate, there are different types that you can put in there that could cause problems. All right, so it's all said and done after you're doing the static and dynamic checks. There's no way the person's going to be able to get through this PR without the code coming out something like this. There's another way you could do this too. You could put in a compile time static check. I think it's static assert. That would do a type check on string to make sure that it is in fact a const char star. Therefore, if the user were to put in like a null pointer as the define, then it would fail to compile because the static check would say, hey, we're looking for a const char star. This code is a slick way of doing the same thing. This is in fact a compile time check, because you can't concatenate a null pointer in here. You can only concatenate a const char star. So the compiler itself is doing that check for us, and this basically has the same effect. All right. So, and I mean, this is basically where we're going to hold off on the example. This is about as good as this is going to get. But there are other things we can do, and we have these all integrated into the Hello World project. So one of them is code coverage. So code coverage, if you're not familiar, when you write your unit tests, the idea is essentially exercise the code. And what code coverage tools do is they'll tell you which lines have been exercised and which ones haven't been. It can be extremely helpful if you're trying to make sure that all of your source code is being properly exercised by your testing framework. The downside here is that, in my experience, there tends to be a lot of code that adding unit tests for provide little, if any, return on investment. In fact, it could be argued that it's like a negative return on investment because you're generating code that really is pointless. So a good example is you might have a piece of function that's doing something very trivial, and the compiler or the coverage tool is saying, hey, you didn't test this. And I can go, all right, I can write a test, but it's doing nothing. All I'm doing is writing this test so I can get the coverage tool to stop complaining. We have a lot of that in Bearflank. So you kind of have to pick and choose your battles here. The other thing I've noticed with these tools is they're all generally difficult to get set up, and there tends to be really poor support in C++ for these. So these coverage tools work great with a lot of other languages that have actual first-class support for testing, which C++ doesn't really have. So for example, GCC will report when you have partial tests. So for example, if I say like if I equals 0 or I equals 1, do something. Well, if I only have a unit test that exercises if I equals 0, that's technically partial coverage because you didn't test the other test case, which is I equals 1. The compilers like GCC and even Clang tend to report false negatives all over the place for these types of partial supports. So you generally tend to just have to turn them off. Oh yeah, so LLVM actually tends to be a little better with that, and it'll actually show you I have different instantiations of this template and you didn't test this version of the instantiation, which is like mind-blowing. But it does matter. There's a difference between a double and an int, and you can end up with weird problems with doubles that you wouldn't see in ints. So you can, but if you've got a project with 100,000 lines and you're changing it all the time, going into it and saying ignore this line, is going to take you about as long as it did to actually go and write the test. So in my experience, it's been all or nothing. You either test everything or you don't test, or you just don't use these tools. They can sometimes be helpful if you want a quick glance to make sure that code was actually being tested, but in general, what matters more is that you're meeting your functional requirements with your tests. So the idea of being able to validate that the APIs are being properly fuzzed and that you are actually meeting all the functional requirements you have for a particular API set as well as the product itself. That return on investment with your unit tests and your functional tests and your integration tests are much higher if that's what you're focusing on than trying to obsess over getting perfect coverage. But once again, sometimes your customers are going to tell you, you have to do this. And that's fine. If you're like we have with Bearflank. So if you end up in that situation, these tools can be fantastic at helping to make sure that you have that, and then you can actually provide it as a body of evidence for accreditation or anything you might be using it for. Documentation is also another thing. If you happen to be using automated documentation tools like Doxygen or Sphinx, you can integrate these into your CI as well, and this Hello World has that integrated. And they're good at finding all sorts of various different issues like, hey, you didn't document this function, or you're missing parameters or return types or whatever. So if you happen to be working on a project where you have pretty extensive API documentation using this stuff, getting this into your CI is extremely helpful because you don't end up having to wait till the end of a release and then go through all the documentation and run your tools and fix all the docs. You're doing it periodically with each PR, which is fantastic. And once again, with this, very easy to do on a small project. Can be more difficult on a larger project if you have errors galore. But once again, if you're really that picky about making sure your API docs are done right, maybe not a bad thing to just turn on and get done. Just depends on how important those docs are to your project. All right, so what's missing? So API fuzzing is one that's not here. API fuzzing really can't be done in a CI environment unless you're doing it like, say, weekly or monthly. API fuzzing takes a very long time to run, like days, weeks. I've seen fuzzers that ran for 2 months and then a minute later test is or a failure is found. So it just depends. There's also some other tools that are starting to show up, things like finding includes that are messed up, like you have too many or not enough, or that kind of thing. We don't have that integrated into the Hello World. Might not be a bad idea. The other thing is that git diff check looks for added white or trailing white space and the new lines at the end of the file, but we've all done it. We've checked in code that had, say, like 2 lines between 2 functions somewhere in the middle of a file instead of 1 line or something like that. So a tool that can really find just excessive white space throughout the code would be useful. Might be like a cool sed script, right, or something. I don't know. I'm not good with the Unix foo. And then other things could be like comment styles and camel case versus snake case. All those kind of things, once again, would be helpful. These are all things that would be great that project maintainer shouldn't have to actually write a comment about. A tool should be able to tell you. Other tools you might find useful are things like HippoMox for mocking with your unit tests. Unit test libraries like, say, catch HPP, and then the GSL. If you want to try and get C++ core guidelines, you're going to need some sort of support library. Microsoft's is a great place to start. And then I will make a comment for any committee members that are watching this presentation. It would be fantastic if we had first-class support for unit testing and mocking within C++. If you've ever used these tools, it's very obvious that we don't. A good example is if you want to use a mocking library, you pretty much are required to mark everything virtual. Well, that's horrible. There's some macro tricks you can play to get around this, which we have in our CI Hello World project, where basically when you're compiling for tests, you have a macro that's uppercase virtual, and that compiles to nothing under production, but it compiles to virtual under test. So that's one way to get around it. That's probably the best way I've seen, but it's ugly. And then there's like 10 million different unit test libraries that are out there. Catch HPP is the best one I've used so far. It's a nice header-only implementation, just like HippoMox. But it's all macro-based. And so if you're doing like lambdas or commas and stuff inside your checks, you get compile errors and your checks or your unit tests end up just looking ugly. Boy, it'd be great if we just had like non-macro-based unit test libraries that were part of the C++ language. We spend so much time as a community worrying about type safety and the core C++ guidelines and all of this stuff because we claim that we have the most safe language to use, but then we don't have native support for actually proving that this stuff actually works with unit testing and mocking. So I think it's something we as a community should probably put more pressure on to say, let's finally get this done. And on that note, are there any questions?
Hi, thank you. This is a great presentation.
Thank you.
I was noticing in the Travis CI, you end up running CMake and make just to accomplish each of the individual steps.
Correct.
Can you comment on why you do it that way as opposed to doing all your checks within the same Travis instance?
Yes. So there's okay, so the question is, why don't I run all of my checks within one Travis instance versus what I'm doing in the example where I do it, one block at a time? And there's actually two answers to your question. The first one is that because I have different tests that I'm running, I have to run CMake different ways. So for example, with the Google sanitizers, I have to turn on one sanitizer versus another, or I might be turning clang tidy on or format or whatever. So that's one reason. The second reason is that if I run them in different tests, then I can leverage the fact that Travis CI will let me run 5 servers for free at a time. And so for every single check, I can basically do 5 tests simultaneously each time. If you happen to pay for their service, then you'll be able to run them all simultaneously. So you can see that with Microsoft's GSL, you'll get their results back in about 3 minutes. And that's all 8 or 10 checks they do.
Kind of a related question. When exactly do you run all the CI? Do you do it on every pull request before it goes into master?
That's a great question. So the question is, when do you run the CI tests? And so the answer is all the above. So that was probably the demo I was going to show, but unfortunately there's not a lot of time. But you're more than welcome to go to the project and you can see where we do this and you can actually see how it works. But the answer is, if you can get it integrated into your PR process, then that's ideal, because that means that you don't have to click merge before all the tests pass, and you can be rest assured that the code you're merging into master or your dev branch, whatever it is you're doing, actually is stable and reliable and passes all your tests. But sometimes, like for example, if you're not using Git has nice hooks to be able to integrate these things in. If you don't happen to be using that, or maybe the tests take too long to build, like Travis CI only has an hour long, or maybe 2 hours now, test cycle. So there might be some constraints there. Then what you can do is you can do it on, say, a nightly basis or a weekly basis or whatever. Continuous integration doesn't say it has to be done at this specific time. It just says that the idea is you should be trying to test as often as you possibly can. So that way you're identifying bugs and integration issues right up front quickly, and you're fixing them periodically over time.
Thank you.
You're welcome.
Hi, thank you for the presentation. My question is about the fuzzer and API fuzzer. What tools are you using? Why are they running so long? And there isn't a recommendation in this area. Thank you.
That's a great question. So why aren't we using API fuzzing? So there are actually different types of fuzzers, depends on your project. So for example, if you're like in CludeOS and you want to fuzz the network stack, you're gonna have to give it lots of external packets. But maybe you're like our hypervisor and you just have APIs and you wanna just fuzz the inputs to those APIs to ensure that it can handle all different types of inputs. The problem with all of these types of environments is that they generally tend to just throw random crap at the APIs. And so for the most part, if you've used these tools before, and I can't remember the name, we don't use them a lot, so I can't remember the name of the one that we were using for a little while there, but it was okay. If you've used them, what you'll notice is that your code only ends up being really exercised by the first couple checks, because the large majority of the junk that these fuzzers are going to send to your code is going to be picked up really quickly. And you got to wait until like the randomizer eventually hits a test case where it can break through all your checks and find that one spot that you didn't do. So depending on how big your code is and how many different iterations it's got to go through, it could take very, very, very long time. Now, that being said, I know there's work to try and integrate artificial intelligence into API fuzzers to be able to provide more useful fuzzing, so you're not just throwing random stuff at it. Once again, I don't know the progress of that, but if there's good progress being made someday, then yeah, we can integrate these in, and it could be very helpful. Thank you.
So a question about check-in and formatting. What's your opinion of when you check in, if there's a formatting issue like whitespace, does change it as part of the check-in versus just warn the user to change it?
Yeah, so we've actually seen that.
Yeah.
And Neil from Microsoft had a great answer to this, which I'm just going to steal, which is that if you integrate it into Git itself, then everybody is forced to do that. And then there are some cases where you might want to click merge even if a test fails. So by doing it through CI, you're forcing, or you're allowing the option to allow a test to fail just so you can get code in. The other reason is that, like, for example, with styling, if in the case of, once again, with the GSL, they use Clang format, they don't use A-style. And Clang format's going to be different on every different dev box. And so if you want to be able to check code in and you make it part of the actual Git patch process, then they're all going to have to use that exact same version of Clang format to get through that. So that's sort of dictating a development environment. And from their perspective, it's Microsoft, they're using Windows, that's painful. So it's better to do it in the CI environment because it's one consistent environment doing the checks, and you always have the nuclear option of clicking merge regardless of what happened.
So in your example, how many times do you recompile your project and other methods to test the exact binaries that will be shipped?
Okay, so the question is, how many times do I test the hypervisor, I'm assuming? Mm-hmm. So we use the continuous integration on each PR. So that's checking unit tests and some functional tests, mostly functional requirement testing. So that's being done on every PR. And you can go to the site, you can see everything that I described here we're actually doing. We also have a Jenkins server. Since it's a hypervisor, we can't do the actual integration and more complete functional testing on Travis CI because they're not going to let you run in a nested environment, since Travis CI is already running in a virtual environment. So to solve that, we have a Jenkins server that runs right now virtual instances using VMware, where we can use nested virtualization, but then we also have physical machines that do that too. Those run nightly, and they actually go and run the actual code the way the user would on their box. And so, for example, we have to have a box set up for Windows 8, Windows 10, Ubuntu, 16.10, the whole 9 yards. It fires off each test every night and makes sure that every one of our environments, everything that needs to be tested is being tested. And every single time we run into a bug, we find some way to integrate it into our unit tests or functional tests or even integration tests so that we never have to manually track down that bug again. It's always in our infrastructure. Mm-hmm. So it costs money, it takes time. You're going to have to convince your manager that, yeah, I can write this piece of code in one day. It's going to take me 3 days to put the testing infrastructure in place to do this. But the reality is that once you have that infrastructure in place, you're going to spend less time as a developer constantly reiterating over the same bugs because you have an automated framework to fix it.
So for each test, for instance, to run a sanitizer, to run Valgrind, you recompile your project for those tests?
Yes. Mm-hmm. Yep, every single time.
Thank you.
You're welcome.
About the formatting, would it be horrible to just allow the formatter to reformat the code and then actually make that the patch?
Yes, so we could do that. It can be kind of complicated to integrate that into the CI process, because what you'd end up having to do is to say, say for example, Travis CI detects that there's a problem with formatting. It would then have to go and check out the patch, reformat it, and check it back in on behalf of the user. And it's kind of, you can do it. It's kind of ugly. Versus basically just yelling at the person saying, oh, by the way, we have a tool called Make Format that'll fix this.
Yeah.
Use it as you're developing.
Yeah, makes sense. Thanks.
Any other questions? Well, I really appreciate your time. Thank you for seeing my presentation.